Hi, Chem students. Let's talk about the liquid and solid, or essentially the idea of getting to a condensed state. So if we look at gases, we know from the van der Waals equation that there was two additional terms that we would have to think about, and that would be the attractive forces, the A term, the attractive forces, and the B term, which is the repulsive forces. So these two forces right here are what control how individual molecules or different gas particles will interact with each other. And if we get to the liquid and solid state, what we know is their interaction is in a certain way. They've come together. And when we say they're coming together, we're really saying that they are attracting to each other. They're attractive to each other, attracting each other. All right, so the key thing is that we're going to come up with some kind of thing that's going to be an attractive force, and that's what's going to hold gases together. And so we're going to give that a name. We're going to call it the intermolecular force. And almost everybody and their brother calls it the IMF for, of course, intermolecular force. So feel free to use that at your discretion in my class at the very least. So this intermolecular force will be attractive, the one that we're going to be dealing with, and it's going to be responsible for creating the solid and the liquid phase and holding the molecules close together whenever they're condensed. So what I want to do is I want to look at some data and see if we can get some trends that will tell us what we need to understand about the force, this intermolecular force, so that if we come up with an explanation, that explanation will have to work for all of these things. So let's give it a try. First, we're going to start by looking at the halogens at room temperature. Very simple idea, but the halogens are fluorine, and that's a diatomic, and chlorine, it's a diatomic, and then bromine, it's a diatomic, and also iodine, it's a diatomic. And what we notice immediately about these is they're all very similar. These are all nonpolar molecules. If you were to go look at their Lewis structures, they're all single bonded. They all look like this, XX, with a bunch of electrons around each one of those guys. So these are very similar, nonpolar. That means there's no dipole moment. So all we're looking at here, the only thing that differs as we go down the line here is their molecular mass. And take a look at this. At room temperature, fluorine's a gas, chlorine's a gas, bromine's a liquid, and iodine's a solid. So what we see immediately from this is that as we increase the molecular mass, we see an increased opportunity for there to be this intermolecular force to take hold. So there seems to be an increased intermolecular force as the molecular mass increases. If we come up with an idea about what this intermolecular force is, it better work that way. We better have a way for this trend to make sense. Let's take a look at another trend. Here's a bunch of molecules and their boiling points given in degree C. And just remember that boiling is the act of going from a liquid to a gas. So the thing holding the intermolecular force together, or holding the molecules together in the liquid phase, would be the intermolecular force. So this actual action is breaking the intermolecular force. So when we go from liquid to gas, when we boil, whatever substance is being boiled, the intermolecular forces that hold together the liquid are being broken. And that's where that energy is going. So what we can say then is, just from knowing that, a high boiling point equates to strong intermolecular forces. All right? And just as we saw before, a large molecular mass kind of increased the strength of those intermolecular forces because solids were condensed. I2 is a solid when it's real heavy. This case is a little bit different. Let's look at the first group here. And as we look at this C2H5OH, then C3H7OH, as we go down right here, we can immediately see we're increasing the molecular mass, and just as we expect, the boiling point is increasing. Why do we expect that? Well, the heavier thing we would expect should have a stronger intermolecular force. All right, so that's what we get. Perfect. We look over here at this at the other side of the table, and voila, as we go down, the molecular mass is once again increasing. And so is the boiling point, and that means so is the strength of the intermolecular force. Fantastic. But I want you to look at one thing here. Here are two molecules with very similar molecular masses. I've actually calculated out that the C5H11OH is at 88 grams per mole, and the C6H14 is at 86. That's not enough of a difference to make a big deal here. But look at the difference in the boiling point, 411 versus 157. So obviously the boiling point or the molecular mass can't be the whole story. There has to be something more that's playing a role here. And what we've just learned is very important. We've just learned that the structure of the molecule matters. And another way of saying that is that's the type of molecule. So, for example, all of these in the left-hand column are alcohols because they have that OH covalently bonded to a bunch of carbons. And then we've got the other column over here, which is on the right-hand side, I'm sorry, and that is a bunch of alkanes. So the question is this always true, this idea that the type of molecule matters, and maybe we can predict what properties that the alcohols have that make them have stronger intermolecular forces than, say, the alkanes. Before I move on, I want you to see one interesting trend here. When there's these similar types of molecules and they're organic like this, notice this difference. As we go from C2H5OH to C3H7OH, we see a difference of 20. We go to the next one, 20. The next one, about 20. We'll go over to the alkanes, same thing, 20, 20, 20. There's a constant change of about 20. That's true whenever we're adding just this. Well, it's not necessarily true, but it's a good trend. Every one of these, the only thing that differs is the addition of a CH2 bonded, kind of stuck in there between two of the other carbons that exist. Just a neat little trend, a neat little trick to have up your sleeve, but you can't just go across and use this universally. It's just true with organic straight chain molecules. So let's look at one more set of data before we move on and summarize all this. And that is, let's look at H2SE, H2S, and H2O. All of these look like this. There's something in the middle with a hydrogen attached to it. All right? And on the periodic table, they're all below each other. So oxygen, right below that sulfur, right below that is selenium. And as we look at these boiling points, as we'd expect, as we decrease, as we go up right here, as we increase the molecular mass, we increase the boiling point. I know that seems weird, but we're going from minus 60 to minus 40. So this is perfect, exactly what we'd expect to see in our trends that we found so far. They're the same type of molecule. They're these dihydrides. And we'd expect that as we go from H2S to H2SE, we increase the molecular mass, and we should see an increase in the intermolecular force strength, and therefore we should see an increase in the boiling point. However, take a look at water. What's going on there? Water has a boiling point of 100. That's way different. It's hugely different. This doesn't make a bit of sense. How in the world can this be the case? Well, so here's the deal. We're going to have to, when we come up with this theory, it's going to have to also include this weird thing. All right? And there might be other molecules that are weird. Whatever we come up with, it better be able to explain all of these. So that's where we're heading next. We're heading towards this. We've just learned that IMFs hold molecules together to form the condensed phases. We know that the IMFs are affected by the type of molecule, and that seems to be the most important thing. Also by the molecular mass. Heck, there might even be a couple other things that we haven't thought about yet. Water is one of these exceptions that we have to make sure works. And there might be others of those as well. So any theory we get that describes how intermolecular forces equate to the properties of these molecules. And by properties, I'm talking about things like surface tension, viscosity, melting point, and so on. We'll get to those later. Any theory we get better be able to describe all of this. We want one idea to describe it all. All right, so that's where we're heading here in chapter 11. We're going to talk about what these properties are of liquids and solids, and can we explain them with one straightforward theoretical idea.